So, Craig, why aren't you doing the band thing today?
I have plans.
You have plans? Okay.
They they just rescheduled it yesterday, and we were supposed to have it today and tomorrow, and we were supposed to get back today at 5 o'clock before they rescheduled it,
Yeah.
and yeah, I can't do it because the concert starts at 6, and so we wouldn't be out of there until like 7:30.
Yeah. Because all the way up in Bath County, too, right? Yeah. Well, I guess the first thing you do is you check to make sure it's indeterminate, which it is. So 2 times 3 minus 6 over 3 squared minus 9. Okay, so it is indeterminate. So you take the derivatives, and you get 2 over 2x. So it's just 2 over 2 times 3, which is 2, 6, just 1/3.
It was 7:38. Like, oh crap, I must have missed it.
Okay, so is that what you guys got? 1/3? So you take the derivative of 2x is 2. Derivative of 6, negative 6 is 0. Derivative of x squared is 2x. At this point, if I plug it in, I've removed the indeterminacy. And so for the next one, you know, again, if you plug in x equals 3, you'll find out it's indeterminate. You get 0 over 0. So you just need, I'll do the derivative of the denominator. I'm so nice to you guys. Okay, back to handing out papers for a while. So remember use the chain rule on the square root thing. I don't know what that buzz is. So remember you changed the square root to the 1/2 power. So it's the exponent times the exponent reduced by 1. So actually so when you rewrite it as x plus 1 to the 1/2 power, when you take the derivative, you get 1/2, the exponent, times the same quantity, x plus 1, raised to 1 less than the old exponent. So you subtract 1 from 1/2, you get negative 1/2. You take the derivative of the term inside the parentheses, which is just 1. So that's the chain rule part. The derivative of negative 2 is 0, and the derivative of x minus 3 is just 1. So at that point, you don't have indeterminacy anymore. So what you end up with actually is the limit as x goes to 2 of 1 over 2 square root of x plus 1. So this dividing by 1 means it's just the numerator, and this disappears, and this goes to the denominator. So then you can just plug in 2. So it's just going to be 1 over 2 times the square root of 2 plus 1, which is 1 over 2 times the square root of 3. Did I do something wrong?
Yeah, I think it says the approach is 3, so you'd add
Part-
4.
What's that? Oh, it's to 3. Yeah, I was thinking something was wrong because I never expected a square root. So I was about to, when you said that, I was thinking I did something wrong. So it's yeah. Thank you for pointing that out to me. So it's to 3, not to 2. Can't read my writing. So we get 1/4. Okay. Now the next one, the derivative of e to the x is just e to the x. And you know how to take the derivative of polynomials. So you'll have to do it twice to get rid of the indeterminacy, which in this case is infinity over infinity. Yeah, usually those ones that go to infinity are either 0 or undefined. It's hard for one going to infinity that involves 2 different kinds of functions. If it was just a ratio of polynomials, then yeah, you can get a number. But when it's dealing with different kinds of functions, the question is ultimately which one goes quickest to infinity, and that's the one that is going to drive the whether it goes to 0 or it goes to infinity. So I saw in the paper last night that you're losing a chemistry teacher. Did you know that? Was that public knowledge? Mrs. Mutersbaugh is going to resign at the end of the year. Did you see?
Well, it is now.
What it is?
It's public knowledge.
It's followed, yeah, because it was on the school board, the thing. Yeah, that's a shame. Yeah, so every time the paper comes out with resignations and appointments, we're always like, what's going on? So do you know what she's doing next year? Is that public knowledge? Do you know what she's doing next year?
I think she's going to Lord Botetourt, maybe?
Yeah, okay. I just wondered whether that was public knowledge too. If you didn't say that, I wasn't going to say it, but since you said it, it must be known. It's hard to find a good chemistry teacher. So the answer is it's undefined because just because I know e to the x increases faster than pretty much any polynomial at some point, but you take the derivative, first derivative, you'd get that, which is still infinity over infinity, so you do it again, and so then you get e to the x over 2, and then when you stick in infinity, you get e to the infinite power over 2, which is basically infinity, because the infinite part is in the numerator. If it was the other way around, if you had 2 over e to the infinity, it would go to 0. And I told you that, so the derivative with respect to x of the arc sine of x is equal to 1 over the square root of 1 minus x squared. So now that you know that, if you didn't remember it, you probably remember it more from the integral. We know the integral of 1 over the square root of a squared minus u squared involves the arc sine, so it's not surprising that well, it's not surprising, it's just obviously the derivative is what it is. In the case of this last example, which I didn't write on the board, but you got on your paper, in that case you end up with, I think, 0 over 0. So it's a kind of the traditional version of indeterminacy. Okay. So the answer on that last one is 1, because when you plug 0 in, you after you've taken the first derivatives, you get 1 over the square root of 1, which is 1. Yes.
Yeah, I have one of those.
Oh, sorry. Yeah, you came in late. That's right. Let me give you one here with a hole in it.
Thank you.
And let's look at that function. So the function that we're looking at the last case is the arc sine. Oh, yeah, Christian needs one too. Oh, here's your test from the other day. So it's what was the problem here? Oh, it's the arc sine of x divided by x. So looking at that function, it looks like a little smile, doesn't it? But you can see that it looks, the function does not exist at x equals 0, but you can't tell that from the graph because it's infinitely small point. But you can see that it intersects the y-axis at x equals 1. So that is the correct answer. That's funny. That's a interesting smile. Okay, so you can turn those in at the end of the period. So we're going back to chapter 8, section 8. Oh, did I tell you when? So yeah, I forgot. I started telling you when the next test was. So my plan is to have it the Tuesday after Easter. Are you guys off, or did you lose that because of snow?
I think we're off.
They can't, well, for at least for our county, they can't take away our actual spring break. They only take away the Friday before spring break.
Okay. So when is your spring break?
It's the first week of April.
So you get the whole week off? Oh, okay. Okay. So I guess I could do it next Thursday. That's before spring break.
We're both coming.
Yeah. The Thursday before spring break.
Coming on spring break too.
Oh, you are coming on spring break. Yeah. I mean, is there anybody who's not going to be here the Tuesday after Easter? I mean, most of you should be here anyway, so we'll make it Tuesday after. That'll give you a little more time to prepare. I could do it next Thursday, but it's a little soon. I usually like to leave a little buffer in there, more buffer than just a day or two. So what day is that? So it's that would be April 3rd. So the test on Chapter 8, April 3rd. Okay, so the last thing we have to talk about in Chapter 8 is this improper integrals. And we looked at two cases. We looked at the integral from 1 to infinity, 1 over x squared, and the integral from 1 to infinity, 1 over x. And we found out that the integral of 1 over x squared has a finite area underneath that curve, whereas the integral of 1 to infinity 1 over x dx has an infinite area. So some improper integrals converge. They give you a finite number, whereas some diverge. That's when you get infinity. So that's one class. There's also some improper integrals. Instead of the limit going to infinity, the function goes to infinity. So, if you look at the function 1 over x, as x approaches 0, so let's just plot, we'll look at so we'll do 1 over x. There's two things that happen with that. One is that as x approaches infinity, the curve approaches the x-axis. But also, as the function approaches 0, the function goes to infinity. So that's the other kind of improper integral. Either the limit goes to infinity or the function goes to infinity. But it's the same kind of procedure. You use this limit definition kind of thing, the limit of the integral. And here we substituted b for the infinite upper limit. When we have the other case, we look at which part of the integral goes to where does the function go to infinity. So if the function went to infinity at this limit, then you let that limit be b instead of being the actual number. So we'll show you how that works. So let's look at if we want to know what the integral is from 0 to 3 of 1 divided by the square root of x dx. And if we go to the graphing program here, we look at that function. So instead of 1 over x, we look at 1 over the square root of x. It looks very similar to what we just looked at, except it's kind of skewed. It's a little bit further off the x-axis, and it's a little bit closer to the y-axis. But the function does approach infinity when you approach x from the positive side. The function does not exist at negative values of x because we can't take the square root of a negative number. So what we're looking at here, so let me just grab a picture of that. So this problem is asking, what is the area underneath the red curve between x equals 3 and x equals 0? So that's what we're looking for. So because the function goes to infinity at x equals 0, we rewrite this as the limit as b goes to 0 of the integral from b to 3 of 1 divided by the square root of x dx. So we just carry out the integration as we would normally do, except instead of having a number for one of the limits, we have a variable. So the first thing that we normally would do is replace the square root of x with x to the 1/2 power and then move it to the numerator. So the equivalent expression here, using fractional exponents and making sure that the exponent is associated with the term in the numerator, we get that. Okay. So then we integrate it. We use the power rule. So we'll get x to the positive 1/2 power. We add 1 to the exponent, divide by the new exponent. We put our limits of integration in there, which are b and 3. Then we actually plug in those two quantities. So dividing by 1/2 is like multiplying by 2, so we'll get 2 times the square root of 3 minus the square root of b. So we evaluate the function at the upper limit. The function x to the 1/2 power is the square root. So we get the square root of 3 minus the square root of the lower limit. And at that point, you evaluate the limit. And there's no indeterminacy here, so we just can plug the number in. So we'll get 2 square root of 3 minus the square root of 0. So we get 2 times the square root of 3. So that's the area underneath that curve. So our upper limit, where we draw this vertical line, can go out anywhere except to infinity. If we went to infinity, then you'd end up having kind of a double. I guess I've never seen it happen, but if you actually went from 0 to infinity, you'd have two cases of issues with, I don't know if you have to use like 2 limits and substitute 2 variables in there. Nobody ever does that. So anyway, as you move out here, what that does is it just affects this number, and the area gets bigger as you move this vertical line out. But it does have a finite limit. And it's the same concept of which ones worked and which ones didn't work the other direction. We went back here and we saw that 1 over x squared did have a finite limit. 1 over x did not have a finite limit. If I did 1 over the square root of x from 1 to infinity, I would have not a finite limit. It would be undefined. And it all depends upon how quickly the functions approach the x and y axis. So if I plot these 3 functions, 1 over the square root of x, 1 over x, and 1 over x squared, and I look at both how they approach the x-axis and the y-axis, you can see 1 over the square root of x approaches the x-axis slowly, and hence it has enough area to make the area go to infinity. 1 over x, which is the blue curve, has just enough. It doesn't quite go to the x-axis quick enough, and it's infinite. But the green curve approaches the x-axis fast enough that it is finite. And you can see they switch places when you go towards the y-axis. The green curve here, which went to the x-axis most quickly, is the one that goes to the y-axis least quickly. 1 over x goes about the same amount to each one. So 1 over x doesn't work for either case. It has an infinite results. Whereas the red curve, 1 over x squared, the green curve, which was 1 over x squared, the one that's the red curve here, 1 over the square root of x, we just showed that it does give you a finite answer, but the green curve would not, and the blue curve would not. So there's a rule you can, applies. So let's just do the 1 over x and show that it also doesn't work going the other direction. So in this case, well, I already did that one. We don't need to do that one. What we'll do is we'll do it from 0 plus to 2. Okay, so what we would say, in this case, it's not because we're going to have an infinite limit, but we have a limit where the function goes to infinity. So we take the limit as b goes to 0 plus of the integral from b to 2 of 1 over x dx. So when you integrate 1 over x dx, you get the natural log of x. So we get the natural log of x evaluated between b and 2. So we plug those in. So we get the natural log of 2 minus the natural log of b. Yep. And when you plug in 0, you'll get the natural log of 2 minus the natural log of 0, but the natural log of 0 is negative infinity. And so you get infinity basically. Therefore, the integral of 1 over x dx from 0 plus to 2 is undefined, infinite. Can't spell undefined. Undefined. If I do it for 1 over x squared, I'm going to have the same thing. I'm going to end up with one of these terms is going to be go to infinity, because I'll end up with, when I integrate this, I get negative 1 over x. So when I plug 0 into 1 over x, I get 1 over 0, which is infinity. So I'm not going to do that one. Okay, now this is where we use L'Hopital's rule. There's one particular example where you have to use L'Hopital's rule, so we're going to work through this one. So it says, what is the integral from 0 to infinity of x times e to the minus x over 2? So you see the function. It's defined at x equals 0. Doesn't go to infinity. So there's definitely some area underneath this curve. And the question is, does this curve approach the x-axis fast enough as x gets larger to keep the area bounded instead of going to infinity? So because we have one of the limits infinity, we replace that limit to infinity with b and take the limit as b goes to infinity. To solve this problem, anybody know what technique we would use from chapter 8? So what have we learned? Partial fractions, well, there's no fraction, so it's not going to be that. Trig substitution, there's no square root of 1 minus or plus x squared, so it's not going to be that. Trig integration, well, it's not going to be that because there's no trig functions. What's the only other thing we've done in chapter 8? Yeah, integration by parts. And that involves the product of two terms. So what we're going to do is actually do integration by parts over here. I'm just going to do the indefinite integral, and then I'll plug it in once. I'll plug it into here once I complete that process. So remember, integration by parts is you have to say part of it's u and part of it's dv. U is the part of the product whose derivative is simpler than the original function. Well, if I take the derivative of e to the minus x over 2, it's going to involve e to the minus x over 2. Hence, that's not going to be simpler. So it probably makes sense to choose u as x. Also, dv is the most difficult integral that's in the tables already, which it is. Okay, so the other part is dv. So we need u and we need du, we need v and dv. So to get du, we take the derivative, which is 1 dx. And the integral of this, remember when you have an exponent, you divide by the exponent when you integrate. You multiply by the exponent when you, or the derivative of the exponent. So to reflect the chain rule. So what I'm going to do is I'm going to divide by negative 1/2. So that's the u substitution part. And then I would have the same function. So that's the answer when you integrate that. So remember, the integral of e to the 2x dx is equal to 1/2 e to the 2x. So here the exponent is negative 1/2 instead of 2, so I divide by negative 1/2. So I'll end up with negative 2 e to the minus x over 2. So that's v. So once you have u and v from the original equation, and you calculate du by taking the derivative here and the integral here, you write out integration by parts. It says the integral of u dv, that's my original integral, is uv minus the integral of v du. So you just plug the things in there. So u is x, v is negative 2 e to the minus x over 2. And then the second part is the integral of v, which is negative 2 e to the minus x over 2. So that's v, and du is just dx. So before I integrate, I'm going to just clean things up a little bit. So the negatives cancel out. The 2 comes out front. And I just have the integral of e to the x negative x over 2 dx. Okay. So I just did that integral here. It's the same integral. So what I'll end up with is 2 times negative 2, same thing I got here, negative 2 e to the x over 2 plus c. So the final answer is negative 2x e to the x negative x over 2 minus 4 e to the minus x over 2 plus c. So that's the integral that I needed to do. And so when I come back here, I'm going to plug it back in here now. I'm going to drop the arbitrary constant because I don't need that for a definite integral. So what I'm going to do is I'm going to put the answer here. So it's going to be equal to the limit as b goes to infinity, and the integral was negative 2x e to the minus x over 2 minus 4 e to the minus x over 2 evaluated between 0 and b. Let me just check to make sure I didn't make a mistake here. So that's true. That's true. That's true. Okay, I think it's right. So that's the integral of x e to the minus x over 2 is negative 2x e to the minus x over 2 minus 4 e to the minus x over 2. So now you're going to plug in the upper limit and lower limits. So if you plug in the upper limit, well, let's plug in, yeah, let's do that. Okay, so we get negative 2 times b e to the minus b over 2 minus 4 e to the minus b over 2. So that's plugging in the upper limit. And then I subtract, plugging in the lower limit, which is 0. So I'll get negative 2 times 0 times e to the minus 0 over 2 minus 4 times e to the minus 0 over 2. So I'm evaluating the upper limit, subtracting, evaluating at the lower limit. This is 0. here you get e to the 0, which is 1. So you'll get negative 4 times, or negative times negative 4 times 1. So that part's going to end up being 1. We'll do that. Here, you let b go to infinity, and you'll get e to the minus infinity, which is 0. So this part's going to go to 0 because you get e to the minus infinity, which is 0. So what we're left with is two terms. The first one here, which is negative 2b e to the minus b over 2 and plus 4. So I got rid of the two terms that are going to disappear when you let b go, well, this one goes to 0 because you evaluated the lower limit at 0. Here, this one goes to 0 because when you plug b equals infinity and you get e to the minus infinity, which is 0. So we just have the first and last terms. Now if I plug infinity in here, I'll get infinity times e to the minus infinity. So that's e to the minus infinity is 0. So I have infinity times 0. So that's another kind of indeterminacy. But and it's not a quotient, so I can't use L'Hopital's rule in this current form, but I can rewrite it. So if I rewrite it as the limit as b goes to infinity of negative 2 times b divided by e to the positive b over 2. So I just move this to the denominator. Then I have infinity over infinity. Okay, so that's an indeterminate limit. Therefore, we have to use L'Hopital's rule. So we'll do that separately, and we'll plug the answer in back here in just a second. So the question is, what is the limit as b goes to infinity of b over e to the b over 2? I'm just going to do this part because I'll just take the result here and multiply by negative 2. Well, because it's infinity over infinity, it's indeterminate, so I say, oh, okay, I need to use L'Hopital's rule. So I get 1 divided by 1/2 e to the b over 2. So now it's not indeterminate anymore because the numerator is 1, which is a number, and the denominator is b to the infinity, which is, or infinity over 2, which is still e to the infinite power. So when you plug infinity into the denominator, you'll get infinity. Okay, so you get 1 over infinity, which is 0. So this term goes to 0 as well. So the answer is 4. So the area underneath that curve is finite, and it's equal to 4. And really, the area, if I had x times e to the minus just x instead of x over 2, it would be some other number that's an integer. All the other terms still fall out. Let me just show you that. Let's say instead of looking at the function, so here's the original function was x times e to the negative x divided by 2. Okay, so it looked like that. If I change it to x times e to the negative x, you'll get something that looks like that. That's the blue curve. So it looks like if the exponent is smaller, instead of negative, well, instead of being negative x over 2, it's just negative x, you get a smaller area. And if I did x times e to the negative 2x, you get the green curve, which actually is, that's, yeah, it's even closer, right? Anyway, they all have, this one has a finite area, so these have to have finite areas. They're just going to be smaller. my guess would be that this area is a fourth of that area, and this area is a fourth of that area. Just because you end up with this, when you take the derivative twice, you get, or the integral twice, you get 4 instead of 2. So the whole idea here was that yes, there are other functions other than just 1 over x or 1 over the square root of x or 1 over x squared, which we can evaluate with one of the limits being infinity. This particular example requires you, when you evaluate the limit, it ends up with an indeterminate result, and if you didn't have section 7, you wouldn't have been able to do this problem. That's the gist of it. So I'm going to assign the homework from this section. Somewhere here. Where are they? There they are. So those will be due next Friday. I'm also going to assign some additional problems, review problems from this. There's a review problems in the back of each chapter. So once you finish writing those down, I'm going to assign the review problems, which will end up being due at the test. So I'll give you a few more days to do those, but it goes through examples of problems that they'll be like on the test. So it just gives you another opportunity to practice. So usually, just to give you an idea, I usually have one integration by parts problem, 2 trig integration problems, 1 trig substitution problem, 1 or 2 partial fraction problems, a L'Hopital's rule problem, and I can't remember. Sometimes I don't include an improper integral because there's just not enough time to do that. So sometimes I include that on the next. I'll have to. I think I do that just so you don't. There's a lot of material to cover. Anyway, here are the review problems that I'm going to assign. I guess that was last year, March 24th test. Yeah. So. When I did this test before, it was just 8.2 through 8.5. I didn't include any L'Hopital's rule stuff on there, but don't count on it this time. I may include something. So what we're going to be, now that we've finished, well, we'll do a few more problems from the last section. We'll do that on Monday. We're going to move on to chapter 9, which is associated with infinite series. And so it's kind of it's a completely different topic. And I remember one of my students from many years ago, he said he found it one of the most interesting topics, just because basically what we're going to do is we're going to show how trig functions are related to algebraic functions. And they involve algebraic expressions, but you have to add an infinite number of terms to get the exact answer. So it's, anyway, I think you'll find it somewhat interesting. Most of the time is spent on convergence, whether an infinite series is going to converge or not, which means it gives you a finite answer. Now, if anybody wants to, in the time between now and physics, wants me to look at their Kirchhoff's law problems and see whether you set it up correctly. I will do that, and you can turn it in on Monday if you would like to, if you want to make some corrections to that.